This is Tammy, and I am your kitchen table math tutor. On this channel, we'll talk about algebra, graphing. I'll share some study tips that will save you time and stress, and also lots of encouragement, because math can be challenging, but you can do it. In this video, we'll be talking about systems of equations in two variables, and this time we'll be using the substitution method. This is the first of two algebraic methods we'll be talking about. So also in this series, we have solving systems of equations by graphing, systems of equations by the addition-elimination method. That is the second algebraic method that we will be talking about, and also using systems of equations to solve applications. That will be a mixture of the different methods. And really, you could at that point make a choice to use a different method than I am using, and that would be just fine as long as you're getting the same answer. So I am going to go through some of the same possibilities and the vocabulary from the graphing video, but I'm also going to add a little bit to it at the end, because if I just describe my three possibilities, I have two lines that could cross in exactly one place, two lines that could never cross at all and be so they are parallel lines, or two lines that lay right on top of each other. And that's what that third image really represents. It's just that it's very difficult to actually show that on a graphing calculator or a program like Desmos. So you can see it happen, but the final picture looks like just one line. So some of the vocabulary you may ask to use are vocabulary related to solutions would be consistent and inconsistent. If the solution actually has a solution or has many solutions, then that system is said to be consistent. And that is the two lines that meet in one place and the two lines that lay right on top of each other. The parallel lines that never meet are inconsistent. The lines themselves also have vocabulary attached. That is independent if I see two lines, so that is the system that meets in exactly one place, or the system that has two parallel lines, because I'm not talking about solutions at this point. Independent and dependent just talk about the lines themselves. The last system with two lines laying right on top of each other, I only see one. So that is a dependent system. So that was in the previous graphing video. Now on to the more algebra focused solutions. So when I'm just solving by an algebraic method, I'm not going to have a picture to work from. I'm not going to have a graph that I draw. I'm probably not going to have a graph that I see in my calculator either. So I have to know kind of what I'm looking at to know what kind of a system I'm dealing with. So algebraic results, if I get x equal to a constant or y equal to a constant. So that's just like x equals 2 or y equals -5, or just some variable equal to a number. That's probably the one that you're going to see the most often, and that is a system that is two lines meeting in exactly one place. So you're going to end up with an ordered pair as your solution. That is a consistent, independent system. The other two are a little bit, you get a result that's kind of similar, but then you have to make an interpretation. So if I have two parallel lines, I will get an untrue statement. So that is all my variables drop out and I'm just left with two numbers equal to each other. And then I have to decide, is that true or not true? So the example that I have here is -2 is equal to 5. And if I were to get that answer when I was solving this out, I would have to step back and say to myself, well, wait a minute, does -2 equal 5? If it doesn't, if you get a statement that is not true, you have a system with no solution. So this would be inconsistent, independent, and it would be two parallel lines. The result for a consistent system that is dependent, so those two lines that lay right on top of each other, we would still get one number equal to one number, except that now it is a true statement. And this goes for any true statement. So the example I have is 3 equals 3. It could be 0 equals 0, 2 equals 2, negative 15 equals negative 15. It doesn't matter as long as the statement is true. If that is the case, then you have a solution, a system with infinitely many solutions. Okay, so solving systems by substitution. I'll talk a little bit about the rules and then we'll jump in and do some examples. So we want to solve solve for one of the variables in one of the equations. It doesn't matter which one you choose. Now, when we solved by graphing, I said, well, we have to solve for the y variable because to put it into the calculator or to graph using the slope and y-intercept, we have to have it in that y equals mx plus b form. With substitution, it doesn't matter. We could solve for an x, we could solve for a y. It just happens to be whichever one we choose. We have 4 valid options. That seems like a lot, but I'm going to talk a little bit about how we can narrow down those possibilities and choose the best one. Then we substitute the resulting expression into the other equation. So the one that we did not modify, it goes into that one. And then we solve for the given variable. We substitute the resulting answer back into one of the original equations. And then we solve for the remaining variable. And then, of course, we report our answer as an ordered pair. Now, that seems like a lot of back and forth. And it kind of is. But once you see it and once you start to kind of get into the pattern of it, it makes a little bit more sense than to just sort of write it out in words. I will say before we get started on the examples, a lot of students decide that they like substitution better, even though it is a little bit of a longer process than some of the other methods, only because it's a very familiar process. We know this is something that we know how to do. We've been doing it probably since pre-algebra, taking a value and replacing the variable with it. That's really kind of all we're doing here. So let's move on to an example. Okay, in this first example, we are going to solve this system by substitution, and I do have the directions for this written on the screen. Now, I will continue to do this throughout our examples. You may find that you don't need it after the first couple of examples, and that's fine. Some people really like to see it throughout all of them, just so that they can have a structure to kind of fall back on in their minds. Use it in whatever way works for you. I will leave it there and I will try and color code along with my steps, just especially for the first couple, just so that you can see how what I'm actually writing in the algebra is connected to the rules. Okay, so the first thing that we are being told to do is to solve for one of the variables in one equation. Now, it doesn't matter which one we choose. We have 4 valid options. We could solve for either the x or the y in the first equation or the x or the y in the second equation. So the first thing that I want to do, though, is I want to kind of stand back and look at what I've been given. So I've got x is equal to 2y plus 8 is my first equation, and 3x minus 4y is equal to 22 in my second equation. So this first step says I've got to get one of those variables alone. The thing is, I've already got a variable alone. That first equation says that x is equal to 2y plus 8. Now, I like to think of this as being a little bit lazy. I want to do as few steps as possible before I actually start solving. And the reason is not just because, it's shorter or it's lazy or it's anything like that. It's because the more steps that you take before you even start, the more chances you have to make a small error like a sign error before you even get going. So I tend to go the most direct route that I can go. Here, my most direct route is to say that I'm going to take this expression 2y plus 8 and I'm going to plug it into the second equation where the x is, because now we know that x equals 2y plus 8. So my next step says substitute the resulting expression into the other equation. So this part in blue was step 1. In step 2, I'm actually going to make that substitution. So I have 3, and I'm going to put up a set of parentheses where I'm going to put in that expression times 2y plus 8. It is very important that you put the parentheses in because you will have to distribute that 3 to the 2y plus 8. And if you don't have the parentheses, it's pretty likely that you'll forget to do it. I know that for myself, if I don't write things, they just kind of go out of my mind. So I have minus 4y is equal to 22. Okay, so that's my new expression, or my new equation. 3 parentheses 2y plus 8 minus 4y is equal to 22. So now I can begin to solve. So I'm going to distribute my 3 and get 6y plus 24 minus 4y is equal to 22. All right, well, I'm not done solving yet, but I'm getting closer. So I'm going to combine my y's because those are like terms. So I get 2y plus 24 is equal to 22. Now I can subtract 24 from both sides and get 2y is equal to negative 2. And then I can solve for y. So if I have 2y, I'm going to divide by 2. And I will get y is equal to negative 1. So that's the solve. And I have one answer out of that. I have the answer for my y variable. Now my next step is to substitute the resulting answer back into one of the original equations. And honestly, it doesn't matter which original equation you use. I usually use the one that looks the easiest, but it doesn't matter. I'm going to use the first one just because it's first, and also because the x is already by itself. So at this point, once I actually plug in my negative 1, this is just arithmetic. So I have x is equal to negative 2 plus 8. So x is equal to 6. And that was step 5, to solve for the remaining variable. And now I have to report my answer as an ordered pair. So I have 6, -1. I want to make sure that is in parentheses with that comma. And so that is step 6. Now, what if you're looking at that and thinking, okay, well, yeah, that works for the one that you plugged it into, but how do we know that that's actually a solution to the system? How do we know for sure that that works in both equations? Well, we can plug that point in to the second equation. Now, the check is not part of my steps, nor is it part of the answer. So I'm going to put it in its own little box here. And we'll pretend that I can draw a straight line on the screen. So I think my answer is 6,1. So if I put that into both of those equations, I should get a true statement in both. So 6, we think, is equal to 2 times -1 plus 8. And 6 does equal 6. Okay, so in this first one it works, and we expect that it would because that's the one we solved to get it. How about the other one? So 3 times 6 minus 4 times -1, we think is equal to 22. So I have 18 plus 4 is equal to 22. 18 plus 4 is 22. So since I get a true statement from both equations, I am certain that this answer is a solution to the system. Okay, so I have our second example of solving a system of equations by substitution here on the screen. I have my two equations, x plus 3y is equal to 14, and x plus y is equal to 6. I also have the steps on the side of the screen just so that we can see what my path is to solving this. So my first step says I have to solve for one of the variables in one equation, and it doesn't matter which one. So this time I don't have one of the variables solved for already. So I want to kind of see what my best option is. Now I have 4 valid options. I could solve for the x or the y in the first equation, or the x or the y in the second equation. The thing is, there are going to be some of these that are easier to solve for than others. So the first thing that I want to do is I want to ask myself, are there any of these variables that have only a coefficient of 1 or -1? Because those are going to be the easiest to isolate. And looking at this, I have 3 variables that have a coefficient of 1. So I can really choose any of those 3. I kind of don't want to focus on the y variable in the first equation with a coefficient of 3. The reason is, if I wanted to solve that, I would have to divide everything in the in that top equation by 3. That's going to result in fractions. So I'm going to ignore that because I don't want to deal with fractions. How am I going to choose the one that I do want to solve for? Well, I'm probably going to use the second equation, not because there's anything better about it, but because it's easiest to reach when I'm actually writing it out. And I'm probably going to solve for y. That one I don't have a really good reason for, except that I don't like to write y. I feel like it's like when I write it on the screen, especially, it's a little bit messy. So I am going to solve for y in the second equation. So that's going to be my step 1. I will subtract x from both sides, and I get y is equal to 6 minus x. Or you could certainly say negative x plus 6. Okay, so that's first step done. Now I've got to substitute the resulting expression into the other equation. So since I used the bottom equation, I'm going to take that 6 minus x, and I'm going to substitute it into this top equation for y, because now I know what y equals. So I'll say that that is step 2. I have x plus 3, and I'm going to set up my parentheses, is equal to 14. And now I'll take that expression that I found and I'll put it into the parentheses, because I'm actually multiplying that entire quantity by 3. Okay, so that's part 2 done. Now I'm on to step 3, which is the solve. This solve is no different than any other algebraic solve that you would do. I am going to talk through it, but if you are very comfortable solving an equation, you're probably done already, and that's just fine. So I'm going to distribute my 3, and I have x plus 18 minus 3x is equal to 14. I'm going to combine my two like terms, my x's, and I will get negative 2x plus 18 is equal to 14. I'm going to subtract 18 from both sides, and I would get negative 2x is equal to negative 4. I divide by a negative 2, and I get x is equal to 2. Okay, so now I've solved, I've got one result. Now I'm on to step 4. To substitute the resulting answer back into one of the original equations. And I'm going to pick whatever looks easiest to me. So maybe I'll pick the second one, that x plus y is equal to 6. And now I know what x is. X is 2. Again, this is just a standard algebraic solve. If you're ahead of me, awesome. If you want to hear me tell you what I'm doing, I'll do that now. So I'm going to subtract 2. So y is equal to 4. So this was part 4, and 5 was the solve. Now I will report my answer as an ordered pair. So my answer is 2, 4. Well, I should say I think my answer is 2, 4. To know for sure, I would have to do my check. And I know it's going to work in that second equation because that's how I actually found the 4. In the first equation, I could write it out. You don't necessarily have to. So my x value is 2, my y value is 4, so I would have 2 plus 3 times 4, or 2 plus 12. That does indeed equal 14. If you want to write the check, you certainly can do that. That's always a really good thing to do when you're on your test. The great thing about equations is that we can always know if we have the right answer before we ever turn that quiz in or that test in, just by plugging those answers back into the originals. Okay, here we are at our third system, and we have been given 3x minus 7y is equal to negative 40, and 4x plus 2y is equal to negative 8. And this time I'm not going to label all the steps, but I am going to talk through them. So the first thing that we have to do is we have to get one of those 4 variables isolated. And I'm going to kind of go through the process that I went through before. The first thing that I'm going to look for is, are any of those variables already isolated? And in this case, the answer is no. I have coefficients in front of all 4 of them. I will then look for, do I have a coefficient of 1 or negative 1 in front of any of those variables? And again, I don't, not this time. So now I have to make a decision. I have to decide which one of those 4 variables to solve for. They are all valid choices, but some of those choices may be better than others. So I'm going to start with the first one. And I have a very systematic process that I go through for this. And I'll describe it step by step so that if you think it's a good process that might work for you, you can use it too. So what I'm looking for here is very simply the lowest number that I have on a variable. And I'm not talking about signs, I'm just talking about the absolute value of the number itself. So for this first one, I have a 3 on the x and a 7 on the y. I'm going to ignore that negative for just a minute. The reason that I'm ignoring that is, if I try to solve for any variable, I am eventually going to have to divide everything through by the coefficient of that variable. Meaning, if I wanted to solve for y, yes, I would have to move the x to the other side, but eventually I'm going to end up dividing by a 7. Well, 7 divides by 7 just fine. 3 does not divide by 7. 7 is actually larger than 3, which means I'm going to end up with a fraction. I don't want fractions. So I'm going to start with the lowest coefficient that I have, because I know that I'm not going to end up creating any proper fractions just by the virtue of having to divide. So at least if I pick the lower one, I have a chance of getting nice even numbers, or nice having things divide evenly through the first time. So if I want to get that x by itself, I'm eventually going to have to divide all 3 terms by 3. 3 divided by 3, that's just fine. 7 divided by 3, 7 divided by 3 is a fraction. 40 divided by 3 is a fraction. I don't think that that first equation is my best choice, because I end up creating fractions. So let's move on to the second one. And I'm going to do the same thing. I'm going to ask myself, well, of the x and the y, which one has the lower coefficient? In this case, it's the y. So then I ask myself, okay, well, I know, and that's a 2, so 2 divided by 2 works. That's even. 4 divided by 2 gives me a nice answer. And then 8 divided by 2, that would give me a nice answer as well. So I do not end up with fractions at all on the bottom if I divide by 2. Now, some of you may be looking at that 4 going, well, wait a minute. 8 is divisible by 4. And you're right, it is. The thing is, if I try to do 2 divided by 4, that ends up being a fraction. I don't want fractions. So I'm going to say that my y is the term that I'm going to isolate. So 4x plus 2y is equal to negative 8. And my goal is to isolate the y. So the first thing that I have to do is I'm going to move the 4x over to the other side. So I'm going to subtract 4x. And I will get 2y is equal to negative 8 minus 4x. And then I want to continue to solve for y. So I'm going to divide by 2, divide by 2, divide by 2. Here's that step that would create fractions if I used a number larger than 2 to divide by. So if I had been solving for x and at this point I was dividing everything through by 4, I'd end up with a fraction when I divided 2 by 4. So I get y is equal to negative 4 minus 2x. So now I have one variable isolated. And it's not that this won't work if you end up with fractions, it's just that it's a more complex problem. So if you can make your work a little easier, it's probably a good thing to do that. So now I've got to substitute this into the other equation. So I used the bottom equation to solve for y. So I'm going to substitute the result into the top equation. So I have 3x minus 7, set up my parentheses, is equal to negative 40. And now I'll put that expression into the parentheses. So I have negative 4 minus 2x. And sometimes when I've done a lot of manipulation with this, I like to stand back for a second and just ask myself, do I only have one kind of variable in my equation now? And I do. I've got x's. So I've got 3x, and then I would have to distribute to figure out how many x's I have here, but they are just x's. So I know I'm on the right track. So I've got 3x plus 28 plus 14x is equal to negative 40. So I've got 17x plus 28 is equal to negative 40. I'll subtract 28 from both sides. And I will get 17x is equal to negative 68. I will divide by 17. And I will get x equal to negative 4. Okay, so that's one answer. Now I've got to take that answer and plug it back into one of these other equations. And I'll use the second one this time. It doesn't really matter, but I think the second one looks a little bit easier. So I've got 4 times negative 4 plus 2y is equal to negative 8. So I've got negative 16 plus 2y is equal to negative 8. Adding 16 to both sides, I get 2y is equal to 8. Dividing by 2, I get y is equal to a positive 4. So my ordered pair is negative 4, 4. And then I could check that by plugging those in or plugging them in the home screen of my calculator. If I wanted to change these both into the y equals form and graph it, I certainly could. The fact that the first one is going to end up with a bunch of fractions, the calculator doesn't care. So I could check that in any way that I liked. Okay, so this is the fourth example that they're asking us to solve by substitution. Our system this time is negative 4x plus 2y is equal to negative 12, and negative 6x plus 3y is equal to negative 18. So the first thing that I have to do before I can start to solve this is isolate one of those variables. It doesn't matter which one, but one of them has got to be alone. So the first thing that I'm going to do is I'm going to ask myself, well, are there any of those variables that are already isolated? No, not this time. And then are there any variables with a coefficient of 1 or negative 1? And honestly, no, not this time either. So I'm going to have to use my process of looking for that lowest number. And we talked about that a little bit last time. It can seem really complex at first. It seems like there's a lot going on with that. And really, there isn't. So I'm going to just start with the first equation. Negative 4x plus 2y is equal to negative 12. And ignoring the signs, I have a 4x and a 2y. The lowest number is 2. So now I ask myself, well, I know 2 is evenly divisible by 2. 4 is evenly divisible by 2. And 12 is evenly divisible by 2. So I can solve that top equation for y, and I will not end up with any fractions. I'll end up with a nice, simple expression that I can plug into the other equation. If you looked at this and said, well, maybe I don't want to work with the first one because I don't want to have to rewrite it, I want to work with the second one and check that out first, you absolutely can do that. With systems of equations in general, there's more than one way to go about it usually. So our work in the middle would look a little bit different, but the results would be the same. Okay, so I've copied my equation, negative 4x plus 2y is equal to negative 12. I'm going to highlight my y to remind myself that's what I'm solving for. And then I'm just going to start the solve by adding 4x to both sides. So I get 2y is equal to negative 12 plus 4x. That's good, but my y isn't really alone yet. So now I'm going to divide by 2. And I get y is equal to negative 6 plus 2x. Okay, so now my y is completely isolated. I know what y equals. So now I'm going to go ahead and put it into the other equation. And in this case, That's negative 6x plus 3y is equal to negative 18. So I've got my negative 6x plus 3. I'm going to put it in my parentheses so I have a space to put my expression equal to negative 18. So negative 6 plus 2x goes into those parentheses. And then I start my solve. So I'm just going to distribute first. So I will have negative 6x minus 18 plus 6x is equal to negative 18. There seems to be something a little bit funny going on here. So I would bring my x's together. That would be my next step, is to combine like terms, and I'm still going to do that even though this looks a little weird. So I've got a negative 6x and a positive 6x. The thing is, those two cancel out, and I'm just left with negative 18 is equal to negative 18. Okay, so all of my variables have dropped out. That means that this is a special case. Once I know that this is a special case, it is either no solution or infinitely many solutions, depending on whether or not I end up with a true statement. So when I say true statement, I'm talking about this thing right here. This negative 18 is equal to negative 18. I ask myself, well, is negative 18 equal to negative 18? And the answer is yes, it is. This is a true statement. So my answer really is not an ordered pair, because there are infinitely many ordered pairs. I can't write them all down. There are too many of them. So I could either express my answer as infinitely many, solutions, or I could express my answer in set builder notation. Now, some courses will focus more on this than writing infinitely many. Some will focus more on writing infinitely many. It just depends on what your instructor wants to see. So if you're not sure, I would really recommend asking. So to show the set builder notation, that is one of the equations solved for y, usually. So I'm going to use y equals negative 6 plus 2x. And if you wanted to, you could put that into y equals mx plus b form. I don't think it matters terribly. But again, that's something that you would want to ask your instructor to know what they want to see. So I could write it that as 2x minus 6 just to be safe. Now set builder notation says that I need those curly set braces. And apologies in advance because I don't draw these very well on paper, so I'm not sure what they're going to come out looking like on the screen. So just do your best with those. And then I'm going to fancy it up a little bit. So I've got the set, which is what those curly braces mean, of the points x and y. And this straight line means such that. So what this statement really says is the set of all points x and y such that y is equal to 2x minus 6. You may also be asked to use some of that vocabulary for this. Since this is a true statement, we do have two lines laying on top of each other. They are consistent because there are solutions, and they are dependent because we can only see one line if we look at the picture. Okay, so here I am at the fifth example, and I have the system 2x plus y is equal to 9 and 8x plus 4y is equal to 32. And I'm going to start the same way that I've started before. I'm going to ask myself, are any of those variables already solved for? No, they're not. And then I move on to, do I have any variable with a coefficient of 1 or negative 1? And in this case, I do. This y in the first equation has a coefficient of 1. So that is the one that I am going to solve for. Now, if you're looking at that bottom equation saying, well, gee, everything down there is divisible by 4, why can't I use that? You certainly can solve for the y in the second equation as well. That will work just fine. If I can avoid taking the step of dividing by something, I do. That's just sort of my rule of I want to get to the actual solve as quickly as I can. So here I have 2x plus y is equal to 9. And I'm going to solve for y, meaning that I have to subtract 2x from both sides. So I get y is equal to 9 minus 2x. And now I'll continue with my process. Now I know that y is by itself, and I know that what y equals, it equals 9 minus 2x. So I'm going to put that into the other equation. So that's the equation that I worked on. The other one is 8x plus 4, and I'm going to make my parentheses, is equal to 32. The 9 minus 2x goes into the parentheses. And then I'll step back and I'll ask myself, well, is that only in terms of one type of variable now? And it is. So I feel very comfortable saying that I'm going to distribute and just solve. So I have 8x plus 36 minus 8x is equal to 32. And then, hold on a minute. Then I would combine my like terms, but, I've got positive 8x and negative 8x, and those cancel out. So that leaves me with 36 is equal to 32. Well, that's kind of like the other one. So now I have to interpret what exactly does that mean? 36 is equal to 32, is it? No, 36 is not equal to 32, so this is not true. Anytime I have an untrue statement, that means I have no solution. These are parallel lines, so they never ever meet. If I want to use some of my vocabulary from the beginning, that would be inconsistent and independent, because I can see two lines. So inconsistent because it does not have a solution, independent because if I were to look at the graph, I would actually see two individual lines. Now, this is really the only way that I can express this answer. So depending on what your instructor wants, you may write no solution. You may use the vocabulary, the inconsistent, independent. You may be asked to describe the graph. It really is just going to depend on how your question is phrased. But unlike the last one, there's no set builder notation or any other way to express this other than in words, at least that I have seen. So, the fact that this was a special case may not be surprising to you because it seems like whenever we talk about special cases, we sort of throw them in at the end and then we show them all at once. And I kind of followed the same pattern, but I want to point out that in the beginning, in the first part of this process, I didn't know this was a special case. I just followed the same rules that I followed no matter what. So if you're presented with one of these, you're not going to know, just because it's the third out of three questions on your test, is this going to be a special case? I would recommend kind of not having that in the front of your mind. Just follow the rules and follow the process. And I think once you get to the point where you start to recognize, oh, wait a minute, all my variables are dropping out, then you can start thinking about, okay, all the variables dropped out. I know that's special. What kind of special is it? Is it infinitely many solutions because I have a true statement? Is it no solution because I have an untrue statement? And just go from there. This is Tammy, your kitchen table math tutor, saying thank you for watching. If you found this video helpful, remember to like, subscribe, and share with someone else who might find it helpful too.